All right, let's do the math. Hope you all had fun listening to the jokes. Maybe we'll keep them. Why not? So math here. That's my name, math. Anyway, let's look at the phasor form of all the waves. Ex, S1. Boy, this is going to be is equal to the amplitude. Ex1, it's an amplitude, so 0 plus times e to the minus j k1 z. Now, remember what this is. K1. Sam, are you ready for K1?
I think so. Omega square root of mu 1 epsilon 1, or 1 effective.
Epsilon 1 effective. And we know what this is. Omega root mu 1 multiplied by
Epsilon 1 prime minus j epsilon 1 prime prime.
Right, and the same for the other k's that we'll need. That's a j.
That's a j.
That's a j. Good. Now,
Green j.
how about EXS1 minus? Well, what's going to happen here is we're going to have EX1, so it's in medium 1, and it's minus. What do I do next?
Copy that term.
Exactly.
With the sign flip.
Yeah, so I have less work to do because it's just going to be that. And it's clear what the electric field is for material 2. E plus x. 2, 0. E to the minus j k2 z. So k2 would be all these things with 2's in them. And now let's do the magnetic fields. So by the way, this is x component only, so it's going along the x-axis, and the h is going out of the page in the y-axis, so let's do this. H x s1 plus is equal to what?
That divided by
Eta 1.
1.
Eta 1 is equal to square root of mu 1 divided by epsilon 1 minus j epsilon 1 double prime prime. There we are, all square rooted. OK, so let's do that. That's pretty straightforward. E plus x1, 0 divided by eta 1 times e to the minus j k1 z. H, and that's not y, x, that's y. It's in the y direction. H, y, s1 minus. That's a reflected one. What's that equal to?
Well, we just said it's going to be a reversed sign, so negative of EX1 naught minus divided by eta 1 plus j k1 z.
Well, we're almost running out of space, but we'll manage. So we need the last one is h y plus s2 is equal to
EX2 naught divided by eta 2 e j k 2z.
Wow, I'm getting tired here. My hand's tired of writing. This is a bit of a mess. This is the hardest part, actually. So what do we know? Well, we know the material, so we know all this stuff with the K's. And we know the material, so we know all the stuff with the etas. And we know what this is, but we don't know what that is.
We don't.
And we don't know what this is. So this is related to reflection, and this one's related to transmission. So we're going to have to find transmission and reflection coefficients so we can compute the amplitudes, just like we did for transmission lines. But we need some conditions. So we have two unknowns. So we need two conditions. And we got to use those conditions. By the way, the nice thing about it is that when we apply the conditions at z equals 0, all these terms will be e to the 0, which will be 1. So we'll only be left with conditions on the fields involving these three amplitudes, or the amplitudes divided by the characteristic impedances. So we're going to get two simple conditions, but how we get the conditions, we have to say where they come from. And this is really important because these two conditions are what give us reflection in general. So time to erase.